let's look a little bit of pump impeller trim and just make sure you understand some of the new codes and how do you trim an impeller, what's involved. So here we go. We've got this system out here. We're going to use this system sizer on. System with a system size. I hope you understand where we're going. Design flow by the engineer is 650 GPM at 76 feet of head. But you know what? Pumps are stupid. They don't know that your design head is 76 feet ahead, and they just might run at some other number. Let's just see what happens in this case. Let's turn the pump on. Here's the pump. Charles, a 1510 full DC pump. The green star is where it's been designed by the engineer. 650 GPM, 76 feet ahead. Where are we? About 83% efficiency, midpoint. Beautiful selection of a pump. Great selection of a pump. Will the system run there? Let's turn the pump on and see what happens. So what size motor should we specify? By the way, I think I'd put a 20 on this to be non-overloading. I think I'd put a 20 horsepower to be non-overloading. So system is now installed and running. Let's check out the pump flow. Let's see what really happened. So I got a pump. I want to read the differential pressure across the suction and discharge tappings on that pump to see where it is on that pump curve. So our pump is generating 63 feet of head. Differential pressure across the pump, when I just turned it on in that system, is 63 feet ahead. I like a pressure gauge that gives me differential pressure. Here's our gauge that's made at actually for water specific gravity of 1 that shows feet of head. And it's got multiple tappings to it, as you can see. So I have one tapping to the suction flange, one tapping to the discharge flange of my pump, and I get differential pressure in feet of head. One easy way of getting it if you don't understand the difference in PSI and feet of head. Let's go back to my pump curve. That green star was a design, 650 GPM at 76 feet ahead. Beautiful selection. My pump's not running there. Where is it running? It's running where the red star is. It hasn't been balanced. Nobody's done anything to it. We got too much pump head. Where does it wind up running? Well, it says we have 63 feet of pressure drop across my pump. I have a 9.5-inch pump impeller. I have to be on the pump impeller. So when I go to the left-hand column where my 63 feet ahead is, run a line straight across to my pump impeller, which is where the red star is, I wind up with 63 feet ahead, and I'm flowing 850 GPM. I am flowing 850 GPM at 63 feet ahead. My design was 650 GPM at 76 feet ahead. System will work, but it's going to use a lot of extra brake horsepower. You may have some zones that are noisy, the velocity is so high it may be a problem. So how do we balance this? How could the system size help us? What can we do? Well, remember that scale 5 on the B&G system size of the manual one, or the CD charts in the Windows-based version where you put in the known and unknown flows and heads. That's where these square charts come in handy. We're going to plot a system curve. We're going to put a system curve on this and see what happens. Reality, we're flowing at the red star. That's the real system curve. The green star is where we thought it would be, but it's not there. So let's take a look. So let's go back and let's try some simple solutions like we normally would do. The first thing a mechanical contractor would probably do here is throttle the triple duty valve back, and we can back the pump up the curve and get back to design flow. In other words, all we're going to do, and I think this picture shows it, we're going to throttle. The little yellow chart shows you, and I'll show you this again. We're running at the red star, and all we're going to do is throttle back on a triple duty valve. We're going to add head. We're going to add friction loss that's not there to force the pump back up the curve so that we're at the design point where the green star is, 650 GPM and 76 feet ahead. That's pretty much the way people like to balance and run off and leave. Does that work? It works. Will the system work? The system will work. What's the problem? We actually saved a little bit of money, didn't we? We went from 17 brake horsepower, 6 cents a kilowatt hour running continuously, $8,000 to $7,400, and all we did was throttle the triple duty valve. And now I'm at 16 brake horsepower. I'm running at design. What's wrong with that? You're wasting a lot of money and you're not meeting the code. That's what's wrong with it. We need to trim the pump impellers or put a variable speed drive and slow this thing down. We know we have too much pump head. Why would we run around wasting energy if we don't have to? So let's use our system sizer to see how we might go about trimming this pump impeller to reduce the horsepower required and save some additional money. Remember, we're at 16 brake horsepower. That's where we are right now. So what does ASHRAE 9.1 2010 have to say about this one? Take a quick look. Hydraulic systems shall be balanced proportionally, and impellers shall be trimmed or the pump speed adjusted or variable speed drive to meet the conditions. There are some exceptions, 10 horsepower or less, and there's some exceptions about the savings, but in this particular case, we're going to easily have to do it. And I'm going to tell you, most jobs need this done. So how are we going to go about this? Well, what do we know? We know the real true operating point is 850 GPM at 63 feet ahead. So we know in the real world, the operating point is 850 at 63 feet ahead. Let's do a system curve for that. Let's graph the system curve. So we go to scale 5, the magical CV scale 5 with the manual sizer, or the CV charts of the Windows-based versions, and we plug in 850 at 63 feet ahead. What do you know? Your known flow, 850. Your known head is 63. And what are we after? We would kind of like to know what head we need at 650. That's design flow, right? We're pumping 850. We kind of like to know what it would be at 650. Now, you know what we're really after is to meet the design need at 650 GPM. So all we got to do once you plug that in, you set that up, and we just go to 650, for example, on this particular screen, and you'll see we need about, what, help me out here, about 36, 37 feet ahead to do 650 GPM. And we pull these particular numbers off, any set of numbers you want to. In this case, we pull them off this way. 650 is 37, 750 is 49. This is this magical square chart right off the system size of scale 5. What are we going to do with this? We're going to plot a system curve. And I took each one of those points, little red stars, and I plotted my system curve. That's the real curve. That's where the real world is. That's where we're really operating is 850 GPM at 63 feet ahead. But we're pumping too much water. Wouldn't it be nice to save some money here? So what do we do now? How much flow do you want? The design flow was what? 650. GPM at 76 feet ahead was design flow. All we do is do a little vertical line, and where that vertical blue line crosses the red system curve is our minimum impeller size required to give you 650 GPM, which I think you're going to find is about 37 feet ahead. But notice the brake horsepower. What are you saying, Chris? I'm saying to you that the brake horsepower is dropped. We've gone from a 9.5-inch impeller, not a half-inch impeller, down to what looks like about maybe 7.5 roughly. And the brake horsepower is probably going to be 7.5, 8 horsepower. So we cut the operating cost significantly. In fact, let's just summarize this. 7.6-inch impeller trim. Look at how much money we have saved by trimming that impeller and or using a variable speed drive and slowing it down. A variable speed drive does the same thing as trimming the pump impeller. You just dial the speed down. I've gone from 17 brake horsepower at initial startup to 7.6 brake horsepower. I've cut the operating cost in half. Now do you see why ASHRAE says you got to do this? And now you see the power of the system size in helping you do these calculations and making sure things are done right. Based on 24 hours of operating costs at 6 cents a kilowatt hour, you see the savings potential. And now I think you understand why ASHRAE wrote this in the standard and why DOE is saying this is going to become the energy code for every state in the union. Ladies and gentlemen, we appreciate your time. Remember, this Windows-based version of the system size and the little iPhone versions are online and they're free. For you old guys like me, and I'm an old guy with gray hair, I do like that manual system sizer. The limitation of the manual system sizer is it's only good through 12-inch pipe. Another limitation has nothing to do with MPSH on it. So I would strongly recommend you guys get the Windows-based versions and you spend some time with this. You cannot find a more important tool for every engineer, every contractor, every young person coming this industry to learn. You need this desperately. Have a great day. Thank you for your time.